Okay.
Thank you. Sorry.
All right. And actually, there'll never be one right answer because it's not a well-posed problem you could answer right. But I will discuss the most recent state-of-the-art among mathematically oriented economist statisticians and epidemiologists. And I'm going to do it in the simple case of point exposure study. And we want a general approach to many problems. Key steps are going to be doubly robust estimators, machine learning, to estimate outcome regression propensity scores, because remember those are regressions, that's what machine learning does. And we're going to talk about sample splitting needed to use ML algorithms and cross-fitting after sample splitting to recover efficiency lost by sample splitting, and then higher order influence estimators to further reduce bias. And then we're going to discuss, after all this, some philosophical issues. Do the new methods violate the urban legend that confidence intervals after data-driven confounder reduction are not valid? And an issue to keep your eye on is, does mathematical understanding ultimately help in controlling confounding? Okay, so I'm going to go straight to hypothetical data. So I have AY of X on N people. And A is a binary treatment, Y is a binary continuous outcome, X is a d-dimensional vector of baseline covariates, and D can be much, much greater than N, that should be big N. And IID data means they're just a random sample from some near infinite hypothetical superpopulation. It's just the usual way you think about it. So we're interested in causal effects. There's the counterfactual data, the Y you would have had if you weren't treated, the counterfactual Y you would have had if you were given treatment equal 1. Those are counterfactuals. I'll use capital letters for random variables, that is things that not everyone in the population has the same value of, and a small letter to represent possible values. And here's the usual link between the data. People who are treated, the Y they see is their counterfactual Y corresponding to being treated, and their counterfactual Y according to not being treated is missing data. That's consistency. Okay, and ignorability is that that treatments independent of your counterfactual given your covariates. That basically means there was a randomized trial given X. That would be true in a randomized trial where the randomization probability is dependent on X. We have an observational study, so we're going to assume this by assuming nature ran a randomized trial given X. So the only difference of the trial is we don't know the probability of treatment given X, and the probability of treatment given X, that is the probability A equal 1 given X equals little x, which is for A is binary, it's the same as mean of A given X, therefore it's a regression. We write as the propensity score is pi of X. So you might estimate the propensity score by a logit model if X only had 2 covariates. Fitted by logistic regression, that's the probability of treatment. And at each level of X, association is causation if I have no confounding. And the treatment effect at a level of X, if you have no confounding, that is the mean of the counterfactual outcome among people with X equal X when you're treated minus the outcome when you're untreated, is just association. It's the mean of Y in the treated at that level of X minus the mean of Y in the untreated at that level of X, which if you've had a simple X might be something like that. In fact, we're going, for the purpose of this talk, so we're going to assume that the treatment effect's constant over X, because that's not the main point of this talk, so it makes it much easier. Okay, so that is the treatment effect at each level of X is a constant, tau 0. And it turns out if A is binary, tau 0 has a particular form. So I'm going to let B of X be the regression of Y on X, the outcome of X. And it turns out that it's the mean of Y minus its regression on X times A minus its regression on X over the mean of A minus its regression on X squared. Okay? And the only thing you have to remember for the talk is B of X and pi of X. The propensity score and the outcome regression. Okay, so we're going to concentrate on the numerator, again, to simplify things. And the reason I'm using this rather than the average causal effect is the formulas are so much easier. Double robustness, all these exotic things are just fall out like they're trivial. Okay, so the numerator of that was the mean of y minus its regression given x times a minus its regression given x. And that's, as you under the null, this guy is 0 with no confounding. So now how would you estimate this? Well, I don't have population data, so whenever I see an expectation, I check a sample average. And whenever I see something I don't know, I estimate it. So this is some estimate of the propensity score, and this is some estimate of the mean of y given x. That's pretty obvious. And how good is this estimate? Well, we usually measure, at least in terms of bias, the good of an estimate by its mean minus the thing you're trying to estimate. Remember, I'm calling the numerator psi. So that's our parameter because tau is the ratio, and I'm forgetting the bottom. Okay, so, and you can do algebra, and it's got the bias as an interesting form. It's the mean of the true regression minus your estimate times the true propensity score minus your estimate. And now you know what a double robust estimator is, that being 1. Because notice, if your estimate happened to be the true one, you get a bias of 0, the true outcome regression, or if your estimate of the propensity score happened to be the true one, you get 0. And that's what we mean by doubly robust. The mean 0. You have no bias if either you get the outcome regression or the propensity score right. It doesn't matter which one, and you don't have to know which one. That's a doubly robust estimator. Okay. Now, we have to estimate v of x and pi of x, right? Remember, those are the only things we don't know. So we're going to, okay, we could use a parametric model for v of x and estimate it by least squares. We could use a logistic model for pi of x. Only one must be correct. That's the beauty of causal inference. It's because you only get confounding of x is associated with both a and the outcome y within levels of exposure. And that's sort of why doubly robustness is possible, because there's 2 ways to control confounding. And so the next question is, okay, you want to control confounding. Now you've got billions of covariates out there, all this genomic data and stuff. And do we simply add more and more covariates x to make ignorability more likely? Okay? Well, hopefully you have some substantive ideas as to the confounders, but still your dimension's really high because you don't want to forget things. Now, throughout, I'm assuming by choosing maybe many covariates, some of which aren't confounders, that you've controlled confounding. You don't know which ones are important, but that is, you have a randomized trial run by nature within levels of x. Now, that's not always true. There are reasons that adding covariates can create bias or worse bias. One's called M-bias, is when a covariate, you're unbiased without a covariate, you add it, and now you're biased. And another one's called Z-bias, and that's where you're already biased, but if you add a covariate, it's much worse, the bias. And we're not going to discuss those. Those aren't about how to analyze data. That's about identification, worrying which covariate you get. We're going to assume we have, a randomized trial run by nature within levels of x, okay? And people worry about pi of x equal being 0 or 1 because that's a propensity score and you have poor balance and not positivity and so forth. But in fact, because we've assumed the treatment effect's constant over strata, that's actually not a problem for us because it'll just not worry about strata. Our estimator doesn't worry about strata where there's not both a treated and untreated. So that's because we assumed constant treatment effect. So, but now we have big B and pi, and big X. So you have to estimate B of X and pi of X some way non-parametrically. That's in quotes. If you use a parametric model with 1 billion parameters, we call that non-parametric. Okay, it's just that, okay. So a common thing historically in statistics has been to use splines or kernels to do this estimation. And if you do that, let's say we're using splines, you not only need your D covariates, but to get the regression right, because there may be interactions, you better put in higher order, products of them and so forth, and powers. And by the time you put a lot of those in, your actual number of covariates in your model, which is the one that matters, is much, much greater than n, in general, if you're in one of these situations, and D is large. Okay, so, and so OLS and logistic regression, our first two suggestions, they can't even be run on the computer. It just says, won't do it if the sample size is, the number of parameters is greater than the sample size. Okay, so we have to use what's called regularization, like the lasso or machine learning, which, okay, so, so I'm going to describe why you need to use our estimator if you're going to use machine learning. First, we'll discuss machine learning, okay? Oh, no, first I'm going to do it abstractly, apparently. So remember, this guy is our doubly robust estimator. Only look at the bias. We call that bias second order because it's the product of the error in estimating B times the error in estimating pi. Now, if we're going to use machine learning, we have to use a doubly robust estimator. All doubly robust estimators, it's not the only one, have second order bias. That's the key fact. The bias always looks like that. Okay, so what is ML? First, what is ML and why use it rather than simple regression, logistic regression? Well, if you look at the bias, it's going to be very small, which is what we want. If this error, you did a good estimate of estimating the propensity score and a good estimate of estimating the outcome regression. Again, remember what these are. And machine learning algorithms, mainly developed in computer science, are much better at estimating these regressions than ordinary parametric models, kernel smoothing, or polynomials. When you have large sample sizes, when you have lots of data, okay? So some of the ones you've heard are lasso, support vector machines, kernel machines, regression trees, BART boosting, random forests, and now all you hear about is deep learning, which are many layered neural networks. And there has been remarkable progress. If you think of deep learning, a deep learning model usually has several billion parameters. It's not the way you used to think about parameterization. So it's good to estimate any conditional expectation, both our model, using machine learning. However, the functions returned by machine learning, the estimates, have completely unknown statistical properties, at least at this point. So the question is, here we have just computed something whose statistical properties we don't know. Exactly how are you going to get how are you going to measure its uncertainty? Okay, that's the problem, because we're using black boxes. Machine learning, probably, nobody knows how deep learning works. They're learning more and more, but no one really knows. So this is going to be the main issue. How are we going to form confidence intervals after we do that? Well, the first key idea to being able to do that is sample splitting. So we're going to have to use sample splitting to estimate these nuisance regressions. I'm calling nuisance, I mean, every time I say regression, it's either the propensity score, it's the propensity scoring the outcome regression to construct efficiently, asymptotically, consistent, asymptotically normal estimators. That is, things you can form walled confidence intervals with. Why? Because we want to avoid correlation between the estimated regression functions and the thing we're computing, the final form, remember, of our estimator, the sample average of the y minus b hat, a minus b hat, because we don't understand anything about the statistics of these crazy things coming out of these programs. So we don't want to mix those up with our estimator. So what we do is the following. We take our sample size n and we split it randomly into two parts. One we'll call an estimation sample, we'll compute our estimator, and the other we call either a training or nuisance sample, where we're going to compute our two regressions. Okay? So we take half the sample and get b hat x and pi hat of x using some fancy ML method on half the data. Then on the other half, we just stick in these guys in our estimator, but this is estimator on half the data, okay? Okay, then if we do that, because there's no mix-up of people used to estimate this with the people we're doing the estimator on, under weak conditions, our estimator, the W is asymptotically normal with the correct mean, provided that the bias, remember that's the bias, is less than the standard error. Standard error is a 1 over the square root of n, right? Variances go to 1 over n when you're doing a sum of IID things. So we need the bias to be less than the standard error. That is the key fact we need for this to work. And the reason you all see that is because, you know, think of a confidence interval, your hope is centered. If the bias is twice the standard error, the confidence interval is going to be sitting over there. It's not going to cover the truth more than 1 or 2% of the time. You have to be, so you want the bias less than the standard error, so when you move around, it's going to cover, in hypothetical repetitions, it'll cover at the right rate. You don't want to be systematically biased, but what does systematically biased means? It means a larger bias than the standard error, because that's how you're measuring the uncertainty. It'd be crazy, okay? That's what a confidence interval does. It's the estimate plus 0.96 plus minus 1 times the standard error, and the standard error is 1 over the square root of the sample size. Okay, so we need that. So then we're going to look at the walled interval, the estimator plus 1.96 if it's a 95% interval, standard error. And if the bias is less than a lot less than the standard error, this will cover at the right rate, and we'll have a correct confidence interval for the uncertainty, which I'm going to assume you know why that would be good if you want to tell people what you know. Okay. Now, how can we do that? Well, it actually turns out, because we're doing non-parametric regression, you can never have this error less than 1 over the square root of n. That is, 1 over square root of n is called the parametric rate. You can't ever do non-parametric regression as good as you can do parametric regression. So this guy can't be small enough, nor can this guy be, because they're doing non-parametric regression. But if you use a doubly robust estimator, you can be unbiased because you get the product. And if you estimate them each at rate end of the quarter, or minus quarter, that's slower, further away, their product can still be very close, and therefore you get a valid confidence interval. That's why you have to use a doubly robust estimator, because you have to have a product, or you don't have any hope to begin with, okay? Now, notice we've lost half the sample size already because we did splitting. We only calculated our estimator on half the sample. So we'd like to recover the efficiency we lost. So what we do is we take our estimator and add it to the estimator that we get by just changing the names of the validation sample and the estimation sample and the nuisance sample, and do it again, and then average them. Okay? And that recovers the efficiency, and it's still, everything's fine, provided the bias is of one of them is, both of them are less than the standard error. And I just did twofold sample splitting. This is just saying you can do more, better in practice, but theory, to understand this doesn't matter. Well, what if the bias is greater than or equal to the standard error? I use 1 over the square root of n as the standard error because it's roughly of that order. Well, then this CrossFit estimator is not normal. The confidence interval is wrong, and things don't, you know, your claim that this is a 95% confidence interval is not true. It's hypothetical repetition may cover 10% of the time, 0%. Okay, so what we have to do is prove to you that would like to know that that's bias is less than the standard error. That's our whole goal. The problem is since we don't know the true parameter, we have no way to know that bias. Or to put it another way, since we don't know the true regressions, how are we going to know how big that error is? So usually that's all people say. we just hope and pray that the bias is less than the standard error if we use double robustness. So I'm going to show you a weird thing that we can kind of estimate the bias and find out if it's sometimes if it's too long. This is a subtle point. I'm going to try to explain it. And the reason we want to do this is obviously the best machine learning methods may fail to give predictions that are sufficiently accurate for that bias to be one of the squared event. I mean, when you have that many covariates, it doesn't matter what program you have, you'll often not get good estimates, right? Because it's very hard to deal with that many covariates. So how do we do it if the bias is unknown? And so this above discussion right here leads to the following questions. Can tests be developed, the ability to detect whether the bias of a I'll call it double robust using machine, DRML estimator is of the same or greater order than its standard error of order 1 over the square root of n, so that nominal 1 minus alpha 95% confidence intervals cover? If yes, correctly at their nominal rate. If yes, if we do the test and it rejects, can we construct new estimators that are generally less biased without refitting, modifying, or even having knowledge of the ML algorithms that have been employed, or essentially requiring any assumptions at all? In particular, we want to do it without making any assumptions about the smoothness or sparsity of the function class. So the way people say, I'm going to use this algorithm, even before there were black boxes, which no one understands, but in the old days they'd say, well, if it's this smooth or this sparse, my confidence interval covers. But who knows if it's that smooth or that sparse? That's nice to say, but it doesn't tell you anything. So you'd like to be able to test it without making any assumptions at all. And the reason we should be able to do it without refitting, modifying, or even having knowledge of the ML algorithm is it's a black box anyway, so we'll just take what you give me because I don't know what it was doing. Okay, so that's the point. Okay, so the answer to both questions is yes. This is like what the research is on, by using higher order influence functions, tests, and estimators. But something interesting. So you imagine I have confidence interval. Well, you're going to see it in a minute. So let me, how much further is this? Just so you get a feeling of what we're doing. Okay, so we did a simulation with a sample size of 2,500, and we were going for 90% confidence intervals. And we used a spline basis. We used 2,048 spline bases. So which is close to the sample size. We're using less than the sample size, which is important in some ways. And I'm sorry, I'm getting ahead of myself. The thing about the spline basis and Kaggle 248 I haven't explained to you yet. I just wanted to focus on the thing I've already explained, the doubly robust estimator, okay? So for 90% confidence interval, we take the estimator and add 1.64 times the standard error, which in our simulation, the estimator was 0.197, 1.64, and the standard error was 0.034, okay? So that was what you'd see in a paper. Then you'd take the data and say, well, what am I going to do? Am I going to be able to tell that person, I'm glad you said it was 95% confident, but actually it has 1% coverage at best. So so I'm going to explain to you this new estimator, this one based on higher order influence functions, which I'm going to explain what this means now. But it's a new estimator, and it has mean 0.006, and standard error a bit bigger than the other guy, but not that much bigger. But and in the simulation, the truth was 0, the truth parameter. So you can see this guy's fine. It's within a standard error of the truth. This guy was off by 6 standard errors, okay? And in fact, we have a test to see whether to upper bound the coverage. And we have a test that says this guy didn't cover more than 1% with confidence 90%. That is, we're 90% confident in cover more than 1%. Okay, so that's interesting, right? So the main point I'm going to get to here is, okay, this is great, looks great. I actually seem to have estimated the bias, which seems like a miracle. But this is the point, which is somewhat weird. Suppose when I did this, I found my corrected estimator was exactly equal to the original estimator. That is, I didn't find any evidence for any bias. What should I say then? Well, that's no evidence at all that there's no bias. The bias is truly unable to be known without assumptions. It can be huge. So what the best you can ever do, which is what this method's doing, is criticize. You can never say anything positive. And as people get older and become curmudgeons, they go from creating things to criticizing. And this is my age-related research. So, but it's interesting that you can tell someone they're wrong, but if you fail to tell them they're wrong, that's no evidence they're right. So let me now try to explain that a little more. Okay, so I said we could have a better estimator. I could tell you how much it undercovered, you know, at least this much. If I did, I could tell you its bias if I found that out. But when the test does not reject, I'm just saying again, we cannot conclude there is good evidence for the null hypothesis. The null hypothesis being that it has the correct coverage of the true parameter, no matter how large the sample size, because there's no actual way to learn from the data. And in fact, the only way you could say anything about that is assuming additional things that you can't test themselves, such as smoothness, you know, about the smoothness or the sparsity of the unknown functions. And again, I've said this, there's no way we're going to have to know the bias in real data because estimates unknown. In fact, we have no way of knowing the bias is not what we'll call order 1. You know, let's say you have a sample size of 1 million. The bias might be order 1, while the standard error is 1 over the square root of 1 million. I mean, it can be terrible. Yet, if we can sometimes tell that it was terrible, but if it's not, we have no idea. And that's because I'm being assumption free. I can only criticize because I'm not making any assumptions. And so it's, you know, this is, people say use, you know, don't use p-values, use confidence intervals. So in these high-dimensional situations, or in low-dimensional, your own models are right, which you never do, it's interesting to understand what people can really say when they say of a 95% confidence interval. And basically, without certain assumptions being true, which are pretty complex to explain these high-dimensional situations, we have no idea the propensity score estimators and the outcome regression satisfied us that you can't guarantee anything. Okay, so I'm going to just quickly tell you what this does, because I'm going to go on to another topic that's even more devastating as a curmudgeon after that. So remember, this was the bias of our double robust estimator, or of the CrossFit estimator, that doesn't matter. I'm going to give you a statistic, which I'm going to call IF2K, that depends on K. The higher K, the better, but we're going to need K less than the sample size. That's a pretty big K if you use sample size. And so this is going to estimate the bias, but not all the bias, because I told you the bias couldn't be estimated. But part of the bias can be estimated. It's going to estimate part of the bias, acknowledging that I don't know about the rest of the bias. But if the part of the bias it estimates is already bigger than the standard error of the reported in the paper, you know, couldn't cover right. You know, won't have the correct coverage. So that's the idea. I'm going to estimate part of the bias. I'll never know about the other part, so it could be as big as you want. But since I know part of it, I can see whether the part I know is bigger than your standard error of the person who reported this guy, a confidence interval based on that guy. And so since this is an estimate of the part of the bias, what I'll call the estimable part of the bias, the only part I can estimate, I'll just take their estimator and subtract off my estimate of the bias, so I have less bias. Okay, and the statistic for the technical is a second order U statistic, and it depends on K, which I'm choosing near N. Remember 2048, an example I gave, of basis functions. So that was my 2048 dimensional spline basis functions, which are, they're like 2048 dimensional polynomials and their interactions and so forth, but they have better approximation properties. Splines are better than polynomials, but it's the same kind of thing. Okay, and I also need to know the covariance matrix, the inverse of the covariance matrix of those basis vectors, which I also don't know. So I estimated by the sample covariance matrix from the sample. That's why I needed K less than the number of basis vectors less than N, because you can't invert if you have P greater than N, the sample covariance, inverse sample covariance rate doesn't exist. Okay, so, and so the amount of bias corrected and the improved coverage depends on the K I used, this, and the estimator. And if I chose a good basis that explains a lot of the leftover bias, I'm going to be able to tell them you did badly, as I showed. But if I chose a basis that didn't explain much of the leftover bias, I won't have any evidence against them, but the rest of the bias I couldn't estimate, because I only could estimate bias based on less than N basis vectors. I don't really know the rest of the bias. I can't say anything. And so returning to this, so this is what they look like. You see the paper, somebody reports that, say, oh, that's nice, but give me your data. I took their data and computed my second order estimate. I computed my estimate of the bias, subtracted it from their estimator, and I decided almost all their estimate was bias. Because I got 0.06, they had 0.197, so I could tell them, oh, actually your bias was 6 times your standard error. And similarly, I can say if bias 6 times the standard error, what coverage could you get if your 6 standard errors off? And because it's a statistical procedure, it has technical things. I could say it's no more than 1% coverage with 90% confidence. I could explain that statistic, but that's what you can say. And there's the statistic. For those who want to know, it's a U statistic. Maybe if anyone wants to know, I'll explain at the end. But it's a particular estimate, and it estimates unbiasedly part of the bias. Okay. Okay. So now the next thing. Okay. So that's bad enough. Now let's go to the worst thing. Okay. So history of Epi and statistics. So there's an urban legend. I don't know if you all know it. We used to talk about it a lot in the old days, but things have gotten different. So if you're adjusting for some vector covariance to control confounding, any procedure that discards some components of X based on data cannot give valid large sample confidence. That's what people used to say. So but suppose now the sample size D is much, so, okay, so let me say something now. Now, rather than criticizing, okay, so the first part was radical in the sense that I was criticizing the usual thing, or the thing people are starting to do, that, after sample splitting and all, using double or less estimators, what people are starting to do with big data. But now, and I criticize that, but now I'm going to go the other way. I'm going to say, okay, let's say I'm not going to criticize anymore. I'm going to say how to think about what's going on with that. Maybe it works. Okay, you'll see what I'm saying. Okay, so I now have the dimension end of the fourth, sample size of the fourth. So I can't do least squares. Let's say I use a lasso as my machine learning thing. Then the estimates will almost always depend on less than n over 2 components of X. So you know what the lasso does? It sets, if you do a regression on more than n covariates, it always returns less than n non-zero coefficients. So that's saying that here, n to the fourth minus n over 2, a huge number will set to 0. So that's essentially throwing out confounders, right? It's saying, I'm not going to worry about those guys. I'm using the data to throw them out, okay? And so when people first started showing that these kind of estimators I've been talking about, the doubly robust ones, just not my fancy thing to criticize them, could be good estimators, that everybody said, no, that can't be, because we learned in urban legend you can't do that. And the point is, that's not, the lasso is correct. And it's because what they're doing is trying to estimate these regressions. It's only, that legend depends on the fact that we used to only talk about parametric models. And if you're trying to estimate something that at the parametric rate, 1 over the square root of n, that's true. But we're not trying to estimate the regressions at 1 over the square root of n, right? We're at best estimating the regressions themselves at a much slower rate. We're just hoping the product of the errors is less. So because it's about estimating the regressions, not estimating a parameter at 1 over the square root of n, it turns out that the urban legend was wrong about that. And it's no problem if the thing's really sparse, but you don't know where it's sparse, and you use the lasso, there really are, most of the coefficients are 0. You don't know which they are. We would have thought, oh, well, in the old days, well, if you test that, that's going to lead to bias and so forth and so on. And it turns out it's not true. The lasso can find those, or enough of the non-zero ones to do a good job of estimating these guys if there's sparsity. Remember, my method, but we don't know if there's sparsity, so that's why we do my method. Okay. So lasso's good, okay? This is the reason, okay? Now, okay, that's sounding good, but now the return of the urban legend. So this is where it comes in. So you get your estimator after using the lasso to estimate B and pi. And you look at the variance of it, you look at the standard error. You can get it by bootstrapping, that's fine. You look at B and pi, and it's just huge. It's of no use to you. That's because, let's say we're estimating the average treatment effect so that you have to worry about positivity. It's just there's not enough information in the data. So even though I use the lasso, and even though the guide, I'm not going to even criticize it here, maybe it is sparse, is centered, but its standard error is just so huge. Still order 1 over the square root of n, but it's constant, it's just huge that it's no use. So what do people do? Well, this is what FEs always do. There's some procedure for trying to get rid of some of X using the data. Now, the standard way, we've already used the lasso, right? Here, so this is they would, look at the estimate you got in the standard error, then you'd throw out some of the data, some of the covariates, not the data, the covariates, and, you look at the new estimate. There's a change in the estimate criteria, and then you'd say if it's not much, I'll use that new estimate, or maybe you'll compare it to how much the estimate changed to how much the standard error changed. So you could say, well, it must have been biased because the estimate, I don't worry about bias because the estimate didn't change more than the current standard error. There are a lot of ways to do it. The one people usually hear about here is, to throw out an X and see how much the estimate changes. But there are a lot of ways in mass stat, too, that are much more sophisticated. And why are they doing that? That's because after they've done the lasso of these DR estimators, they don't like the size of the confidence interval. It's not whether it's right or wrong. They're assuming it's right. They just don't like the size. It's just too big because you adjust it for too many things. Even though you use the lasso, you adjust it for too many things. So then you start throwing things out. But now the standard error you're trying to make less is the actual standard error of your final estimator, not looking at making better estimates of pi or b. It's your actual estimate of your parameter, which you're estimating at 1 over the square root of n. So once you do anything to make to improve your standard error over using non-parametric regression to estimate b and pi, then the urban legend returns. That is, it isn't mathematically possible. So there's something called the semi-parametric variance bound, which is for a given, I give you a given x, I can compute, if I knew all the right things, how much uncertainty at best there's going to be at the end. And basically what's happening is they're seeing that's too big for you, because the bootstrap's pretty good at that number. And so they say, well, let's get rid of some x's correlated with exposure, so it goes down. And they're going to map that by looking how much the change of your actual estimate of the parameter of interest, which is a 1 over square root of n parameter, changes, and that violates, that's logically, mathematically impossible to give a valid confidence interval. So a lot of the math stat literature says, don't do that. These are some of the other things. Focus information criteria, collaborative TML, certain Bayes methods, all are ways other than to throw out x's. Okay, so they say you can't do that, and people get on their high horse, these mathematical statisticians, because you can't get a paper published in some fancy math journal if you do that. Well, now, here's my final thing. So let's say we did that and we threw out 50 covariates, okay? And then we got our confidence intervals down to where we wanted them. And I say to you, and we have like, 100,000 covariates. I say to you, you violated things because before you threw out any, just doing non-parametric regression, you had that big a standard error. And now you threw out some standard error for the parameter you're entering. Now you threw out some to make it smaller. That's not okay because you can't have a true confidence interval. Oh, well, okay, that's terrible. But imagine the real world where suppose you didn't have, suppose they had forgotten to give you those 50 covariates, mixed up somewhere in all these covariates you don't understand. Then you'd say, oh, I have no confounding given x without those 50 covariates. Let's go. I didn't even know about them. And there you go. And then you get that better, improved standard confidence interval because the 50 weren't there. And you say, oh, this is great. And the guy who had the 50 and got that confidence interval by throwing them out goes, oh, you're so lucky you didn't have them. So this is what I mean. You learn so much about math stat, and I'm telling you today more than you'd ever want to know, but maybe someday in the future when everyone is using machine learning and sample splitting, it will matter. But the point is that people pretend there's a pristine way to do all this, as if, unlike being a Bayesian, frequentists have some, we know how to do it and be valid. But if you actually look what happens in the real world, especially when you have high essential covariates, what is considered a valid confidence versus not depends on arbitrary things like where you started and what covariates you collected. And it is the case that if you needed those 50, then obviously doing an inference without those 50 would be biased. But if you didn't need them, it would be okay. But we're saying if I give you the 50, you're not allowed to throw them out because it might be biased. But if you weren't given those, you just hope there wasn't bias and say no bias. That suggests you just should do a sensitivity analysis any time, like always admitting you may have not gotten all the covariates and throw them out, but I don't know how to parameterize, no matter what people say. I don't have any idea how to really do a sensitivity analysis that I believe. So there, if that's not being enough of a curmudgeon, what more did you want? All right, I'll stop here.
Thank you very, very much. Shall we ask questions, or whether there are questions? Comments?
Was that clear? Huh?
Yes, please.
So no effect quantification in this setup, or you're saying?
It just wasn't the issue. This is the issue about direct confound. That has other issues, but not, I didn't need to complicate it that way to make the point I was making.
Yes, please.
If I understood correctly, I said that the amount of bias corrected with your second order influence function depends on the choice of K and a few other things there. How do you choose K, or can you go across a lot of Ks and see which?
So
one
we're
you
actually, yeah, so we're actually working on that. So we want K near the sample size, and you usually have a whole, what they call dictionary, much more than sample size you can choose from. So we'd like a sort of second order lasso, something like that, to decide which is best. And we have some algorithms we're using, but they're not great yet, and we don't know mathematically whether, in fact, we can do better than that. We don't know what the lower bound is, and we don't know if there are gray algorithms. We haven't figured out any yet. That's the biggest open problem. You put your finger on it.
Yes, please.
The estimators that you use for these doubly robust machine learning methods,
But the one, with the second order or the usual ones? Before I added my thing, or just the usual?
maybe both. Maybe this
Okay.
question pertains to both. But do they have the same interpretation as causal effects that you would estimate with just G computation, like not parametrically, or are they?
Oh, yeah, but I'm doing something simple. I was just doing here a point exposure study. It's just, you have to estimate the propensity to score an outcome regression. So it's nothing fancy. It's just, you know, I just wanted to estimate that parameter, you know, that's 0 under the null in a point exposure study with no confounding. I mean, there are a lot of other issues more complicated that would arise in those cases. But you can still use machine learning. I mean, every time you have to estimate a regression, which are in a, you know, you can use it. I mean, it's good to use machine learning to get a big sample size.
Yes.
The name of that implementation is the likelihood principle, or?
No, it's from epidemiology. It's like the change in the estimate criteria, and you shouldn't do it. It was the way I heard it when I was young.
Only net will kill you that way. Any final question before we thank Professor Robbins very much? Jamie, thank you very much.